assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
We are solving question number 65 as within chapter 22. And the information that we have been given is that we have a hexacyanomanganate 3 ion that is a low spin complex. And we are asked to solve by A, drawing the crystal field splitting diagram with electrons filled in appropriately, and B, determining whether or not this complex is paramagnetic or diamagnetic. From the name of this ion, we can determine that we have a manganese 3 plus ion. Okay, that's number one. And number two, we can derive the electron configuration now knowing the oxidation state of manganese. So if you recall, for the shorthand electron configuration, we go to the closest noble gas, follow along with me on the periodic table, and then we fill in the remaining subshells. So 4s2 and 3d5, okay? So pause here because this is actually the electron configuration for manganese, not manganese 3 plus. To determine the electron configuration for manganese, we actually need to recall that for transition metals, the S subshell electrons are depleted before the D subshell electrons, meaning then that we would lose 3 total electrons. Why? Because the charge is 3 plus, and 1 electron from the D orbital. So the electron configuration for the manganese 3 plus ion is, again, going to the closest noble gas, argon, and then 3d4. This is the correct electron configuration for manganese 3 plus. Okay, good refresher there. So what other information can we derive from what is given? Well, we're told that it is a low spin complex. What implications does this have? Number one, this means that the field is strong and that there are few unpaired electrons. Why? Because there is a strong field ligand, namely cyanide, as within hexacyanomanganate, okay? So what this means then is that there will be a large delta, and delta, which we'll talk about in detail on just the next slide, is the crystal field splitting energy, right? And moreover, this crystal field splitting energy is larger than what is termed the spin pairing energy. Again, two concepts that we will explore in detail on the next slide, all right? So let's go ahead and move on to the next slide and start about drawing our crystal field splitting diagram, all right? So the first thing we need to recognize is what type of shape we have. So we have, again, hexacyanomanganate 3, which is a manganese ion complex with 6 cyanide ligands, okay? And this has an octahedral geometry, meaning then that we need to draw a crystal field splitting diagram for an octahedral complex. Note that they can be different depending on the geometry. They do vary slightly, so keep that in mind, all right? So on this axis, then we have energy, and on this axis, then we have our states, our energy states, all right? The first one is a low level state called the T2 state, and there's an upper energy level called the E state, all right? Between the E state and T2 state, there is an energy difference called delta, okay? And now let's write it out this time. So this delta is actually called the crystal field splitting energy. Okay, so now, how many electrons do we fill into our crystal field diagram? Well, we know that because we've already done our electron configuration, which was like so, all right? So we have 4 valence electrons that we need to fill into this diagram, okay? And we can do that one of 2 ways. We can fill in, according to Hund's rule, of course, 1 2, 3, and 4 electrons. All right, that's one way to do it. And the second method is to fill in 1, 2, 3, and 4. We can pair 2 of them. Which way is correct? This is done according to what type of complex you have. We have been told that this is a low spin complex. What does that mean? It means then that there are few unpaired electrons, okay? And secondly, that the crystal field splitting energy, delta, let's do a different color there just so we can see. The crystal field splitting energy, delta, is greater than the spin pairing energy. Okay, this means then, yes, there is some energy required to keep these electrons within the same orbital because there is repulsion. However, it would take more energy to promote this electron to the E states than to keep it here, despite the repulsions that it feels and experiences, okay? So for that reason, then, this is the correct configuration for this crystal field splitting diagram with 2 electrons paired in the T2 state and 2 electrons unpaired. Okay, so then the final question that we are asked, let's move to one more page just to clear it up a little bit here, is whether or not this is a paramagnetic or a diamagnetic ion. Okay, which one? This is purely definition based. So paramagnetic ions have at least one unpaired, keyword unpaired, electron. Okay, whereas diamagnetic have no unpaired electrons. Okay. So what do we have here? Going back to our diagram, we see that we have 2 unpaired electrons. So by definition, then, this is in fact a paramagnetic ion. This is question number 65, chapter 22 solved.